I think everybody knows what Magidor looks like, so I took this picture from recently up in Finland. Magidor with, I think, Menachem Magidor, I'm not sure. Now, I cannot remember when I first met Menachem. Oh, okay. This is one element of contrast with myself and Magidor. I've always felt in some awe, envy, maybe some even less desirable thoughts, but and certainly awe and admiration and thankfulness that he's been around. I was just noticing that Myrna gave what she said was an antithetical description of Magidor in Cardano. And I was noticing that on the timeline that was posted on the outside the room there, that they talked about it, and what their description was that Cardano, well, he hired Tagliano. He took the proof, and he actually did complete the solution, give the full general solution. By showing how to reduce the general form to the one that Tagliano had actually solved. And then the important point here, perhaps, he actually published the thing and did give credit to those two who had come before. So, I don't know historically who is right here. Quite possibly neither one is. But on that view, I think that my feeling is Cardano I might compare with Magidor and myself with Tagliano, whatever his name is. What was that?
Who didn't publish.
Who didn't publish, right. I haven't deliberately kept anything secret that I know of, but anyway, so the title here is, well, no announced title, I guess going along with the same comment. This is a change from what the title was last night there. So I'll start out talking about that, and then I'll say something about what I've talked about before, what it means to be a Chang sharp for the Chang model, and what the sharp looks like. And then I guess if you can stand it, then I'll say something about the proof. I guess I should admit something about the proof. There is no proof written down, so you would not be unreasonable in taking it with a grain of salt. But you'll see that there's some doubt when I do get to stating a result. Okay, so here's my original title. I did start out by reducing the size of the capital letter Z. So the original notion of a sharp for the Chang model is due to Wooden. who has a sharp, which, speaking of not being published, I would very much like to see. It turned out ultimately to be a sharp for a much stronger model than the Chang model, which I'm not sure the details of that either, but it preserves stationarity, which the Chang model does not. And he asked the question, what is actually necessary to get such a sharp? He uses, I guess it seems to vary a little bit, but a measurable wooden cardinal or a measurable limit of wooden cardinals, or what? Wooden limit of wooden cardinals, and which seems a bit much. He was mentioning the lower limit of one measurable cardinal, and when he asked this, James Cumming and Schimmerling were there, and they suggested Gödel's kappa plus extender of length kappa plus omega plus 1. And I thought it would be more than that at the time, but of course they were right. So anyway, I've had some dispute with Wooden whether this is really what one should properly call the sharp for the Chang model. My view was that it was, because this was pretty much an exact replica of Silver's sharp for L. And what really should be looking at is that analog. Wooden was claiming that this is not the real sharp because, well, among other things, it depends on what the reals are. Silver's sharp is unique, of course, because the constructible sets are unique. And, but he pointed out that if you put a wooden cardinal into the sharp, then you can get the theory is unique, and he thought that that would give the real sharp. And it struck me as I was thinking about it here that the analogy is really not so much with the sharp for L in particular, but with the sharp operation. And so really what I'm talking about here is something analogous to the sharp of the particular class of reals. If you're looking at the real Chang model, then it would be the sharp of the reals in the model. But in any way, we should think of something that's giving the sharp for a particular class of sets. And I'm suggesting this, and when I was thinking about it, I thought it would look horrible, but I guess it doesn't look that bad, so I guess it is possible. In particular, the notion of the sharp of 0 makes perfectly good sense. It's not probably the Chang model, but it would be the smallest. Well, assuming you have a mouse with an extender of length kappa plus omega plus 1, then this would be the smallest model which satisfies that it's a Chang model. In other words, it satisfies that V is constructed from the countable sets of ordinals, and for which there is a class of indiscernibles, and it contains the countable ordinals from that model of the indiscernibles. So I'm a little bit ahead of myself here, but this would be, I mean, yeah, it would be the smallest Chang model, which has a class of indiscernibles and the associated structure with that, and which contains all the countable sequences from that set of indiscernibles. One needs the extra countable sequences. So in other words, the indiscernibles are not for L, but they are for the larger. You have sort of a Chang model over a set, well, in the usual case, R.
In what sense, in what sense they are indiscernibles?
I'm sorry?
What is the meaning of indiscernible?
I'll talk about that later. This is sort of tacked on at the beginning and really probably should have come later. But yeah, so I mean, these could extend to what Wooden claimed what he regards as the true sharp. The true sharp, if I remember right, would be I'm sorry? M omega. Okay, I wasn't sure about which, but yeah. Okay, so this would be getting ahead here. You would look at a model M with omega wooden, well, M of the reals and omega wooden cardinals, and an extender of length kappa plus omega plus 1 of the model. And so, well, this looks to me, it doesn't look to me like the sharp, doesn't look to me like 0 sharp or anything sharp. It looks, well, it looks like M omega sharp. So really, I think what you have here is M omega of the Chang sharp of M omega. So I haven't worked much of this out in detail, and it may be that in detail things have to be changed, but that seems to be.
You should be the mouse, which is omega Woodens with the extender on top.
I'm sorry?
You have the first mouse with omega Woodens with your extender on top, and that's going to generate this Chang sharp over any set by iterating the omega Woodens. You don't put the reals in, you don't need to. It's going to be stronger than M omega sharp because the true sharp's got to be beyond ADL of R. M omega sharp is just ADL of R. So it's going to be the first mouse with omega Woodens and whatever extender you have there on top.
Well, okay, you're saying you don't need.
Yeah, but the omega Woodens have to survive putting that top extender on.
How strong is this? A couple of omega.
Yeah, so it's relatively weak. It's much weaker than omega plus 1 Woodens. It's just omega Woodens with this one relatively short extender on top. And that should be the sharp in any reasonable sense. Because any model that sees that, its Chang model is going to elementarily embed into the Chang model, and you'll have indiscernibles for the Chang model. So it's an object that anyway.
We can talk more about it, right? Yeah. Okay, anyway, so now, I guess now I'm starting my talk. So the Chang model is the smallest model of ZF, which contains all the ordinal and countable sequence of ordinals, so we can write this as L of countable sequences of ordinals. It can also be defined as Chang did, exactly like L, but use the infinitary language L omega 1 omega instead of ordinary first order logic. It turns out you get exactly the same thing because essentially in this model you have all countable sequences, therefore any statement of L omega 1 omega can be stated as a first order statement.
Here it will be a little bit, it depends whether you allow, when you do an L-like construction, it will appear in the opposite of the model. But
Yeah.
if you do an L-like construction, another logic, it depends whether you allow infinitely many parameters in the formulas.
Mm-hmm.
So you allow infinitely many parameters in the formulas.
I'm sorry?
You allow, when you do the construction, the definability allows infinitely many parameters in the formula.
Right, so,
If you just allow finitely many, then it's exactly L of R.
no, but the L of, we're looking at L of countable many sequences. So, in other words, in each alpha, you throw in all countable subsets of alpha.
No, that's good. Okay.
Okay, so as I said, I dropped the convention a little while later, but I'm going a little bit short of claiming this actual theorem on this slide anyway. So, assuming that there is an R mouse end having a final extender E, which has length kappa plus omega 1 in M, I keep forgetting whether it's M single slash or double slash, which I want to omit the final extender from. Is that one or two slash?
Depends.
Depends. I think I switch in the middle here anyway. Okay, that's without the final extender, because with the final extender it's all about. Okay, so 0 sharp is the can be characterized as the least mouse with an alpha filter. At its final stage, you have an alpha filter which has not yet been incorporated, but can be applied to that model. And you can take all the iterated alpha powers of this mouse by that alpha filter, and that gives you the set of silver indiscernibles. And we can do the same thing with the mouse here. You just take this final extender E, iterated it through the universe, and the critical points of the iteration are going to be our class of indiscernibles. Now, this is not quite like, well, obviously it's not quite like L. There's a lot more structure in here. And in particular, we're going to have to do some more here. Remember, take the example of L of U, a single alpha filter. Well, if you look at the Chang model of that, U is not going to be in there. There's no reason why U should be in there. But if you take an omega fold iteration of U, and you get a Prickry sequence, which will be in there, and that will give you U. So the Chang model is going to be U together with its, or the omega iteration of U together with its Prickry sequence. So we have to put in the equivalent of the Prickry sequences here. So, what I'm claiming here is true, is that what you want to do is you take that intermediate model, so we've determined the class of indiscernibles just by iterating E, and so for the rest of this, we're going to E now has been mapped up onto the ordinals, so we just cut that off and forget about it. Well, we'll have to remember it at some point, but we just forget about it, and we take all of the ultra filters in all the extenders in the model M omega, and we want to iterate them until we can recover them. Okay, so when can we recover them? Well, Giddick gave the answer to that. The important point, the major point here was that if in the iteration some extender has been iterated omega times, if there is a countable sequence coming up to it such that the extender f is the image of the extender used at that earlier point, then using the fact here that the less than where this is the kappa, maybe I should call it lambda. So assuming that the length of the extender is smaller than lambda plus omega plus 1, which we know that is always true in this model because we took the least, I guess I didn't say, but we're taking the least mouse where this is true. So that first thing says that if something has been iterated already omega times, then we don't have to iterate it again. The second thing says that if the length of f has cofinality omega, I guess better the Dodd squash has length of cofinality omega, then it's going to be a union of countably many smaller extenders, and so it can't. So if all the smaller extenders are already in the Chang model, then the full extender will be. So these are all the things which cannot. Which we do not, that's the list of things which we do not have to iterate, and so we just iterate till that's taken care of. Now, actually, a striking point here is that this is almost all taken care of inside M omega. The only exception is the members of this class of indiscernibles. M omega has no way of knowing which of those have cofinality omega. If those have cofinality omega, then the Chang model will already have the image of E, well, all initial segments. I mean, all the extenders in M omega at that point will already be there because from the iterations of E. And so if M omega is to do the iteration itself, it does have to have an oracle which says which of these places in the set I of indiscernibles it has to take care of. But other than that, it's all internally, it's all inside M omega. And in fact, what that means is that really M itself knows how to do all this. I mean, this can all be described in M omega. The only thing that M doesn't know is what is actually happening at the ultra powers by E. Okay, so the claim here is then that the result of this is going to be the core model of the Chang model. So the observation is, well, first, suppose that no M does exist, then this shows that the core model of the Chang model is going to be an iteration without drops of K of R. And the important point here is that if there is a mouse, then, well, I mean, immediately we know that from Giddick that all the extenders in n omega cut off at omega are members of the Chang model. And this is, I guess this is what I already said, that in the first case, well, that's the first case of the first, the exceptions from the last slide. But so if it's been used infinitely many times, then it's going to be in there. And it occurred to me, I don't know in the first case whether the same iteration will give the Chang model in K of R, just like the case where M exists. I suspect it does, but I won't claim a proof. Okay, so a couple of observations. First, the important point is that the mouse M is closed under countable sequences. So the point is we're taking a minimal mouse. That means it's going to be, sigma 1 projection is going to be onto the reals. And, well, we can conveniently assume that the GCH holds by collapsing the reals onto omega 1. So I may slip and just say omega 1. But, and then on the other hand, we assume that it has cofinality, that the extender E and therefore the mouse has an uncountable cofinality. And so that's going to ensure that any countable sequence is constructible from a countable part of E and therefore is an initial segment here. So M contains all its countable sequences. The iteration K is almost definable in M omega as long as it's told what the exceptions are. And so that means that every member of C can be described in M. I mean, it says you take, basically you have a function which maps on, I mean, this way I've written it there is not very accurate, but you take, given a countable sequences of members of I, you tell M that this is a sequence of indiscernibles, and then you tell which members of this secondary iteration you're using. Remember, that's describable in M. And then that gives you the name. Of course, M does not know a whole lot about it, not knowing E.
What is exactly the iteration K?
I'm sorry?
What is exactly the iteration K? Iteration K, what?
Oh, the iteration K was the one in which to, in order to make all the extenders definable from their countable threads.
Oh, okay.
So basically, you iterate every extender omega times. Okay, so so now what does the indiscernibility mean? And so if we have a closed countable increasing sequence B of members of I, we'll call that suitable. If for limit members of I, well, first it's continuous in the sense that every limit member of every limit element B sub I for I limit is actually cofinal in B intersect I. So, so looking at B, you know which ones have cofinality omega. And now you want to compare two sequences. And it turns out you have to be a little bit careful here. We'll say B is equivalent to B prime if they have the same length, which is obvious. And then for all but finitely many members I less than the length of B, well, first, if B sub I plus 1, if there's a gap between B sub I and B sub I plus 1 and one of them, there's also a gap on the other side. And furthermore, if the B sub I plus 1 is a limit member of I, then B prime sub I plus 1 is also a limit member of I. So I found it rather surprising here that this bit about the finite exceptions. I mean, what happens is you talk about, since you have countable sequences of ordinals, you can talk about the existence of Prickry sequences. And if you have consecutive members of I, then you'll have a maximal, you get maximal Prickry generic sequences for those countable. If you have countably many gaps, then that gives you Prickry sequences at points where you can't generalize Prickry sequences at the point where you can't get them if they're all adjacent. Okay, so here I'm calling it a theorem. If you have any formula of set theory and you have T as a name, B and B prime are equivalent suitable sequences, then C satisfies phi of T of B if and only if it satisfies phi of T of B prime. So that's what I mean by indiscernibles here. Okay, so few corollaries. First, any map from I, just like I, any map from I into I, which preserves suitability, will give you an embedding from the Chang model, an elementary embedding from the Chang model into itself. And you have to be a little bit careful here, I think, but any elementary embedding which preserves terms from the terms I was talking about you get from K, the embedding K, will be of this form. I want to be careful because you could, take the first measure at some point and just take an embedding which moves the those indiscernibles for that measure, and that would give you an elementary embedding of the Chang model, and would not quite be of that, and would not be of that form. The mouse M, this I found interesting. An implication here is that the Chang model is really not very much bigger than L of R. It's bigger by this extender of length kappa plus omega plus 1, and that's it. And its truth depends on the reals, but it depends only on the set of reals. Basically, the only thing you can do to the Chang model without changing the reals is to make members of this set I of indiscernibles singular. So you can do Prickry forcing at a measurable cardinal of V, which happens to be, if it's measurable in V, then it will be in I. So that will make that singular. It'll change the Chang model because it changes the iteration K, but it won't change the theory of the thing, apart from the statement that that particular ordinal is singular. Every member of C is definable in C from a countable subset of I. That's not true, is it? Any member of the core model of C is definable from change that first C there to the core model K of R in C. So that's that's what corresponds to the statement that every member of L is definable from some finite set of indiscernibles. Okay. See, I think I'll cut this short. I guess I'm running out of time almost already, and I started a bit late. So, I mean, what the proof involves first use forcing to define names. And I'm not sure I fully understand why that should be necessary. After all, as I said, we have a perfectly good set of names to start with, but that does seem to be necessary. So we use Magidor's extended-based forcing, like Giddick used to get counterexamples to the SCH. Problem is you can't force over the model M because it collapses right away. And so the obvious answer is that, well, a little bit more, take the initial segments of E which look like E except that they're cofinality omega. That gives you a convenient cofinal sequence of length omega 1, and you force with extenders that initial segment. This corresponds to what I did earlier when I was looking at the stronger assumption that length of E is kappa plus omega plus 1, but in that case the initial sequences were better. So the problem here is that the initial segments of the extenders, I mean, there's no way of saying that these initial segments of M with their final extender are elementary substructures of M with its final extender, because you have this definable sequence of points at which the length of the extender is kappa plus omega plus 1 in the model. So you can't directly give, I mean, just forcing over E delta won't give you names for indiscernibles for all generators over that. Well, but I mean, you can take elementary substructures to get other extenders, not initial segments of E, which do have these ultrafilters. So instead of using this one extender, we take all extenders and do that as a sort of Radon forcing over the sequence of extenders. There is a problem that the restriction M is, of course, not closed under countable subsets. At some point you need this, but you can write this initial segment of E as, I mean, take as a countable direct limit of sets which are countably closed in M, and use all of those in the forcing. Okay, so I'll leave it off there. Thank you for your attention, and if you've forgotten what he looks like. And thank you, and happy birthday. Thank you for what you've been all these years, and presumably will be in these coming years. I'm sorry?
A sharp for L is sort of a smallest witness that we are not in L. In what sense this sharp resembles this intuition?
Oh, the smallest witness that we're not in L. Did I say that?
I said that.
Ah.
Well,
the smallest witness of a large cardinal.
yes.
If you're not
Smallest witness of a large cardinal.
Also,
Yeah.
you know, is not there.
Yes.
Yeah, I mean, it's all somewhat circular, but I guess it's the smallest large cardinal not in it.
So this would have the same properties that we might. Would this be the smallest
Yeah.
large cardinal that corresponds to the smallest large cardinal which is
Yeah.
not in the chain?
Well, that's really what the smallest, that has to be the smallest mouse not in the Chang model, so that's the same thing, yeah.
Okay, so thank you very much. Any other questions?
Is it literally, I want to, is that the smallest mouse which is not in the core model of the Chang model?
Yeah.
And how do we compare mice? In what sense is it smallest?
You iterate them out till they're the ones in
So once you iterate, this is the shortest one.
Yeah, I mean, you're iterating this one mouse.
Okay.
And so all this is one, it's got one final extender. So you iterate out the whole extenders on the class of ordinals. You cut off that extender, and the remainder is, well,
Okay.
is the core model.